Okay. As you've been reading through the book, we have our three circuit elements: resistors, inductors, and capacitors. And now that we have a oscillating power supply, at each instant, the current and the voltage across each of the devices, the current through the circuit, is going to vary. It's going to vary sinusoidally, just like a mass on a spring. So what we assume is that the current has this value. The lowercase value means the instantaneous value. The capital letter here indicates the maximum amplitude, which is fixed. These will both be measured in amps, and then we simply choose the cosine function. If we let this phase difference be 0, then at t is equal to 0, I is equal to I max. And so it just simplifies our plots. Because the resistor is a completely passive device, all it experiences is a potential drop. The frequency of the signal plays no role, and so we can simply write at each instance the voltage drop across the resistor is just equal to some fixed magnitude times the same function. So when I plot it out, if I have my solid line, if that's my instantaneous current versus time, if I start at t is equal to 0, then I simply get this. If I plot on top of it the instantaneous voltage across the resistance, that's this dashed line, what you notice is it doesn't matter what the magnitude is, I just happen to make it smaller. What's important is that when the current reaches its positive maximum, the voltage across the resistor also reaches its positive maximum. When the current drops to 0, the voltage across the resistor drops to 0, and it basically maps out the same curve. So in that case, we say that the current and the voltage across the resistor are in phase. And so in terms of magnitudes, we can simply write the maximum value of the voltage across the resistor is just equal to whatever the maximum current is delivered from the power supply times the resistance. And again, we assume the resistance is fixed. So for resistors in AC, there's not much difference between what's going on in AC with what we saw is going on in DC. But then when we look at the capacitor and the inductor, things do change. So for the capacitor, I leave the current the same. The current is equal to the time rate of change of the charge on the plates of the capacitor. And remember that the voltage across the capacitor is directly related to that charge. So we end up doing taking an integral, and so we get this form. So when we plot out the current, again, if we use the cosine, we get this curve. When we plot the instantaneous voltage across the capacitor, we start with the sine, so we'll get something that looks like this. And so when the current is a maximum, the voltage across the capacitor is 0. When the current is 0, the voltage across the capacitor is a positive maximum. And so we say that the current leads the voltage by 90 degrees. So if time moves from left to right, we see that we reach a positive maximum for the current a quarter of a cycle before a positive maximum for the voltage. So we say that the current leads the voltage. So then we can write out Ohm's law this way. You saw in the book that X sub C is the capacitive reactance, and it's equal to this. We don't use the word resistance even though the units are ohms because this depends on the frequency. So it tells us how the capacitor is reacting to the changing in the current. The more quickly the current changes, the smaller the reactance. Okay, for the inductor, again, we'll use the same equation for the current, but now we have to take the derivative for Faraday's law, so di dt. So instead of getting a positive sign, you get a negative sign here. And so when I plot it out, it'll basically be flipped. So when this is a maximum, this is 0. When this goes to 0, this will be a negative maximum, and so forth. And so now it looks like the current is lagging the voltage across the inductor. And again, that's why a quarter cycle, so 90 degrees. There's Ohm's law, and there's your inductive reactance. So the problem with these types of curves is that they're sinusoidal, and it's similar to what happens with rotational motion in Physics 41. It's sometimes hard to visualize all these curves and arrows. So just like in Physics 41, we take those rotational quantities and assign straight arrows to them, vectors. And we're going to do the same thing here. Instead of calling them vectors, they're called phasors. Okay. And in your book, you probably saw something that looks like this. So we've got what looks like a looks like a Cartesian plane. All we're going to look at are the horizontal components. So the horizontal components, those will give us our instantaneous values for the current, the voltage across the resistor, the voltage across the capacitor, and the voltage across the inductor. Okay. The vertical components, we simply ignore those. Okay, so we're just worried about the horizontal components. So I can draw this as I. We saw that the voltage across the inductor leads this one, and the voltage across the capacitor lags. So we have a 90-degree angle here and a 90-degree angle here. And then the idea is that this entire thing rotates this way, counterclockwise. And at each given instant, if you figure out what the horizontal components are along this axis, that gives you the instantaneous values. Okay, so one way of doing that is to, instead of trying to draw it, is to just do something like this. What I have here is a meter stick. This will represent my current. Remember, the voltage across the resistor is in phase, so I can also write down, right on top of it, V sub R. And what I can do is, since I can't do this on the board, I could simply illustrate as this thing rotates what's going to happen. So it's going to rotate, from your point of view, it'll be rotating counterclockwise. So this will be the current as well as the voltage magnitude across the resistor. This will be the voltage magnitude across the capacitor. This will be the voltage magnitude across the inductor. And so the way I have it oriented now is identical to what I had on the board and most likely what's identical in the book. Okay, so let's imagine what happens when we're in this orientation. Right here, the horizontal component of the current is the maximum, and the voltage, the instantaneous voltage across the resistor is a maximum. What do you notice here is when the current is a maximum, on both of those plots, both of those sinusoidal plots, when the current was a maximum, whether it was the positive maximum or the negative maximum, the instantaneous values for the voltages across the inductor and the capacitor were both zero. If I rotate it around a half of a cycle, I end up this way. My horizontal component of the current is a negative maximum. That should mean that the voltages across the inductor and capacitor are also zero. Okay, so as I rotate this, what happens? If I start in this orientation and rotate a quarter of a way around, what happens? The current starts at a positive maximum, gets smaller, 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 and approaches zero. The voltage across the resistor does the same thing. It starts at a positive maximum. As it rotates, it goes zero, zero, approaches zero, zero, and zero. What about the voltage across the inductor? The voltage across the inductor leads. So as the current gets smaller, the horizontal component of the voltage across the inductor gets more and more negative, gets more and more negative. So as the current approaches zero, the voltage across the inductor approaches its negative maximum. At the same time, the voltage across the capacitor starts at zero, and its horizontal component, which points this way, gets more and more positive. So what's nice about these phasor diagrams is that since you're just dealing with straight lines, this is very easy to visualize, and it matches everything that we talked about with components from Physics 41. What's nice is you only have to worry about the horizontal component and completely ignore the vertical components. And if you imagine this thing rotating and just look at the horizontal components here, you should be able to convince yourself that it matches those sinusoidal curves that we drew initially. So once we get up to here, what happens? At this point, the current is zero. The voltage across the inductor is a negative maximum. The voltage across the capacitor is a positive maximum. As we go this way, what happens? The current now swings in the other direction. It becomes increasingly negative and approaches its negative maximum. At the same time, the voltage across the inductor gets less and less negative and approaches zero. The voltage across the capacitor, which started its maximum, approaches zero from the positive direction. And so the idea is as this thing rotates, if we look in all four quadrants, Each quadrant represents a quarter cycle, and at the end of each quadrant, either the current or the voltages are either 0 or a maximum, depending on the quadrant.